Continuing on with the idea of using active stuff, coming up is Tristan, who many of you, or all of you know from CloudSat Perspective. And I'm going to guess he's also going to talk about merging these things together. Is that true?
That is true. Yeah, in fact, that's I purposely decided to put this image on my opening slide because I want to make one point right up front here. Even unlike Calypso, which has the IR instrument and wide field camera, CloudSat is one of the very few satellites that we have up there with literally just one instrument on it, the CloudSat Cloud-profiling Cloud-profiling Radar. And the vast majority of our products from CloudSat are multi-sensor products. And so when Steve said, he wanted me to talk about CloudSat and the cloud perspective from CloudSat, I came back and told him, I really have to talk about synergy between CloudSat and other instruments because that is kind of how we work and how we think of CloudSat. We think of it as contributing to a bigger picture. So I will talk about CloudSat alone, but I will also talk about some synergies between different instruments. And so this is just a nice graphic that some high-paid graphic design people put together. CloudSat going through a MODIS cloud image of looks like a developing tropical storm, I think this is. And so you see another key point here is, and I'll make this actually on the next slide, that as opposed to most of the talks we've had today so far, with the exception of Bob's talk, where we've been dealing with primarily looking at cloud information in the XY plane, in the latitude-longitude direction, the main point of CloudSat and Calypso is, of course, to look at the vertical structure of clouds, and that was exactly why active sensors were chosen for this purpose. And so we have to sort of shift our thinking a little bit here when we talk about CloudSat and start thinking about, primarily I would say the YZ plane, because we're flying pretty much, we have a very high orbital inclination, and so we're mostly latitude and height. And so most of the plots I'll show, in fact almost all the plots I'll show here will be latitude height cross sections. This is just one example of a CloudSat image, one of the earlier CloudSat images from 2007, showing exactly the kind of information that you get from CloudSat. Basically what I consider to be kind of like an X-ray through the cloud, where you're seeing a convective system there with some fairly thick anvil cirrus clouds probably over on the left-hand side. Some shallower convection underneath that, a little bit of topography there. You can see a few bumps, a little mountain range or something over the middle. And then you have some more precipitating, probably some precipitating and some non-precipitating mid-level and shallow clouds over on the far right. So this is a very nice image kind of showing the full spectrum of clouds that you can see with CloudSat. And of course, it's not too hard, I don't think, for anybody to just look at that first image. And if I asked you where are the clouds in that image, you can immediately with your eye pick out anywhere there's a color is presumably a cloud. And so our most basic CloudSat product is something like this panel on the bottom here, just a cloud mask, where we think there are clouds based on the CloudSat data. Okay, so let me actually start here. I want to start with some limitations sort of right off the bat, since that's what we've been trying to talk about. The first thing to point out, and I think Bob pointed this out as well, CloudSat and Calypso launched in 2006. We do not have a very long data record, so unlike Paul's talk where he had a 40-year record from almost the same instrument, we have about a 4-year record of CloudSat observations, or 4.5 years where CloudSat was operating nominally, and we've added a couple of years since then of daytime-only observations after we had a battery anomaly that stopped the spacecraft from taking nighttime observations. So we have a limited duration record. Also, because we're looking at the XZ plane, or the YZ plane, sorry, we also, and our footprint is about 1.5 kilometers, we have a very limited sort of spatial sample, and we also have a very long repeat time. So as opposed to being able to look at clouds every 15 minutes or every hour, our repeat cycle is every 16 days. And so you're not going to go and see the same cloud system twice with CloudSat and Calypso, unless it's a very big, long-lived system and it moves into another one of the orbit slices. So right off the bat, sort of two limitations of CloudSat. And so that leads me to kind of my first point, my first main bullet point is the CloudSat strength is really for process studies, not climate analysis and not really weather, like data assimilation type applications where you're going to put in regular information and look at the evolution of systems. I will come back to what I mean by a process study here in a second, but that'll hopefully be a theme that comes from this. I think we can learn a lot from CloudSat, but it's not going to be in terms of a long-term data record. I will bring up one exception to that, which comes back a little bit to what Mark was mentioning about our sensitivity to precipitation. We have done a little bit in the climate model evaluation side, I think, which is valuable in terms of that. But I want to come back to, I don't want to spend a lot of time talking about algorithms, but I do think it's important that we talk a little bit about just how CloudSat measurements provide information about clouds. Obviously, if you're going to do process studies, you need to know something about the physical properties of the clouds. And so this slide here just summarizes a few of the main equations here that go into the cloud water content product, which is actually, again, already a combined CloudSat and MODIS retrieval of liquid and ice cloud microphysical properties. The equation that I have up at the top there is basically this assumed size distribution, just a log normal distribution that we assume for these clouds. And the only point I want to make is based on that assumption of a distribution, you have to assume the distribution, which has three parameters: the number concentration, the width parameter, and the effective the geometric radius. Based on that assumption, you can derive an expression analytically for the reflectivity, for the liquid water content, and for the effective radius. So again, without going into any detail, you can see that these three quantities, the observable and the liquid water content and effective radius, can be linked through the parameters in the size distribution. There's another point that I want to make here. Well, so a couple points to make here. So this is the expression for reflectivity, assuming that size distribution. One thing you see, this is another point that Bob just brought up. We have, like I said before, three parameters that describe that size distribution. All three parameters enter the expression for reflectivity, yet we only have one wavelength on the satellite. So clearly we have three unknowns. We have one reflectivity measurement. We have some non-uniqueness issues here. This is going to be a major source of uncertainty in our retrievals. We do benefit a little bit from the fact that these parameters at multiple layers within the cloud are related to one another. We have correlations. Clouds do not just, the effective radius in the cloud doesn't just jump around in the vertical, so there's some linkages there that help us to reduce the number of parameters we have to retrieve by using the vertical structure information. But nevertheless, there's more parameters to retrieve than there are unknowns, and this is one of the main reasons that we bring in MODIS or some other information to try to help improve the retrieval. But even still, that's going to be a source of uncertainty. Just keep that in mind. All right, so this is just an example of a retrieval. Again, not something to talk about a lot, but coming back to our original case, that's the same reflectivity profile I showed before. You see the cloud maps, which I've already shown, and then this is the retrieved ice water content and the retrieved liquid water content. And again, don't want to talk about this very much, other than to mention one more important property, and actually that relates to, let's just go back to this one, the specific sensitivity of the reflectivity to particle size. Anywhere that there's a precipitating drop or a drizzle drop, anything that's a fairly large raindrop in the CloudSat field of view is going to immediately preclude us from retrieving the properties of clouds, because reflectivity, at least for smaller particles, goes to the 6th power of drop size. And so unlike passive observations where if you had a few large droplets around, they're not going to affect the radiance measurement at all. Here, if you have 2 or 3 large drops and millions of small drops, all you're going to see is the large drop, and you cannot do a cloud retrieval. So that's another potential, let's say, downfall of the CloudSat observations, a source of uncertainty. However, we've turned that into a positive by recognizing the fact that this also means that CloudSat is going to be extremely sensitive to where it's precipitating on the planet. And so we've actually developed, after CloudSat launched, after kind of realizing this issue, we've developed 2 products. These are my products, or things that I've been heavily involved in. Well, the name doesn't matter, but the rain profile product, which does rainfall intensity measurements and then retrieves precipitating ice water content and liquid water content through the atmosphere. And then something called 2C Snow Profile, which does exactly the same thing for snowfall. This is work that Norm Wood has been doing. Many of you probably know Norm now. And Mark mentioned this product earlier as well. This is our retrieval, the same exact idea, but retrieving profiles of snowfall rate from the CloudSat reflectivity measurement. So we've kind of taken advantage of this extra sensitivity that we have to particle size to do actual retrievals of precipitation with CloudSat. Okay, so what I want to do is just basically show just a couple of real small examples here of what I mean by process studies with CloudSat. There's a lot of different ways that we've used the CloudSat observation to, I think, get a better understanding of what's going on in the atmosphere. The couple of examples I'm going to show, this is actually the main one. It also emphasizes this idea that it's the synergy between CloudSat and other instruments on the A train that really help us to get some good science out of this. This is one example where we've looked at this great sensitivity that CloudSat has to precipitation and use that to, I think, document for the first time on a real global scale aerosol suppression of precipitation. And so the plot here on the left-hand side shows the probability of CloudSat detecting precipitation as a function of the liquid water path observed by the passive microwave that Mark talked about. So this would be the liquid water path from the AMSR-E satellite co-located with CloudSat. And what we've done is we've taken that information, that relationship between probability of precipitation and liquid water path, and just grouped it into polluted scenes and non-polluted scenes as indicated by MODIS. So basically we've taken MODIS aerosol index and separated out the top 10% most polluted cases and the 10% cleanest cases. The cleanest cases here are shown in the red curve. The most polluted cases are shown in the blue curve. And what you see is there's a clear reduction in the frequency of precipitation, or the precipitation efficiency, as I like to call it, of these liquid clouds when you have aerosols present. And then what we've been able to do, and so to kind of connect these results to the climate problem, even though we can't do climate studies, is we've then looked at the same relationship, but from different climate model simulations. This is the CAM5 model, just the sort of standalone atmospheric climate model simulation showing exactly the same curve. The clean cases shown in red actually agree fairly well in terms of the precipitation efficiency with the CloudSat observations. But what you see is that as soon as you increase precipitation and make pollution, and you make conditions polluted, you get a sudden shut-off in precipitation. The model tends to be way more sensitive to aerosol than it should. In the middle here, we have the multi-scale modeling framework where we embed a cloud resolving model within the GCM grid box. You try to represent the precipitation process a little more accurately. And you can see that having that little bit more direct measure of precipitation processes leads to an improvement at least. There's still a little bit high sensitivity there to aerosol, but at least a much better match with the observations than what you get without having the CRM embedded. Okay, so I said I would make one exception to the rule that we don't do climate studies with CloudSat. The one exception is because we are so good at detecting where it is raining, we have put together a climatology from our 4 years of data of where it rains on the Earth and actually where it snows in total. This is actually precipitation fraction, not just rain fraction. So this is the first, I think, really accurate estimate of exactly the frequency of precipitation around the planet. The passive microwave, due to its footprint, misses some precipitation. The true precipitation radar says that it only precipitates about 4% of the time in the tropics, whereas CloudSat shows about 12%. So clearly there's some limitations in just detecting where it's precipitating using existing sensors. And so we felt that it was necessary to actually go ahead and produce at least our precipitation climatology from CloudSat. And then we went ahead and used that information and, again, tried to evaluate climate models with it. And one thing we showed here from this paper that I wrote with Graham, I worked with Colorado State, Graham Stevens, basically that climate models tend to be drearier than they should be. It rains more frequently, and they have more frequent light precipitation than is observed. We don't need to talk about the details of all these bars. Basically, the main point is, while the climate models get about the right global mean precipitation, they have far too frequent precipitation. And again, so the implication there is they have too frequent light precipitation. That means they may be getting the extremes of precipitation wrong. And if that's going on in the current climate, then you kind of wonder maybe do they have trouble predicting predicting changes in extremes in precipitation in a future climate. Likewise, we've done the same thing with snowfall. So here's another, I guess this is a related calculation that we did. We did our climatology of frozen precipitation from CloudSat. This shows just polar views looking down at the North Pole and looking down at the South Pole of the accumulated snowfall over 4 years of CloudSat data. So this is the annual mean from 4 years of data. And what we find, just for sort of comparison here, the global mean is about 62 millimeters per year, as opposed to about 1,000 millimeters a year of rainfall. So just to give you an idea of the order of magnitude of these things. But again, because of our sensitivity, this is probably the first estimate of the snowfall accumulation that you could really trust. And I will say, we're not the only group that's done this, to be fair. Mark Cooley has done this, Guosheng Liu has done this, so there's a couple groups that have all done it, but all with CloudSat data. That's the main point. And again, we've used this data, not to belabor the point, but we've used this to evaluate the distribution of snowfall and climate models, and this is a paper that we're now putting together with a French Cyril Palerme, who visited us a couple months ago now, probably. Okay, so this is where I want to kind of wrap up. Although I have one more thing I want to show you just after this, but I wanted to put together a little bit of a summary here of what I think the strengths and limitations are. I think the profiling capability is obviously key. That's the main motivation for flying active sensors in the first place. This direct sensitivity to precipitation is a real strength. I'm assuming you're getting that from the fact that I've shown 3 examples now of precipitation. The fact that we're co-located with other sensors is critical, otherwise you don't get much out of CloudSat alone. And so again, good for process studies, but due to the fact that we have a short data record, limiting sampling, including things like limited swath, also the diurnal cycle, very long repeat times, not so good for kind of climate-related applications. And also because it's single frequency, we have large uncertainties in a lot of our retrievals due to the assumptions you need. But what I want to do, just before I wrap up, I want to come back to a question that Steve poses a lot of the time, and actually I think he's got a lot of people in the community thinking about this. Hopefully this will lead into a little bit of discussion here after a while, but I think what a lot of the differences that we've seen now in the different instrument capabilities really does boil down to what is a cloud. And of course this has implications for modeling as well as it does for remote sensing. And we've seen all kinds of different definitions, and obviously the previous talks have done a much better job of kind of outlining the way that the different sensors detect clouds. This is just my very crude way of breaking it down, but you know, some people think clouds are bright, some people think they're cold, other people look for warm signatures over the ocean, like Mark Cooley pointed out. There's of course the calliope, looking at the backscatter at the visible wavelength. And then I've just shown you a lot of information about how CloudSat uses reflectivity observations to detect where clouds are. So my question is, how do we reconcile all of these distinct viewpoints to try to come up with, I guess, the most comprehensive view of clouds we can, and really make the most of this information for science? I think that's kind of the key theme for the discussion coming up. So I'm going to offer 2 solutions. One is what I call the cooperative solution, where we basically cooperate. We take all the information from the different sensors, in this case CloudSat Calypso, and then of course the wider swath that MODIS provides. And we put together as comprehensive of a picture of the 3-dimensional structure of clouds we can. This is actually the basis for an algorithm that I've developed for radiative heating rates in the atmosphere. There we use CloudSat MODIS Calypso. We also use AIRS for temperature and humidity and AMSR-E for surface characteristics. So 5 sensors go into this, all to construct the structure of the atmosphere, which is used as input to a broadband radiative transfer algorithm. And from that, we get an estimate of cloud impacts on radiative heating profiles through the atmosphere, which is really the key way that clouds actually influence the climate system. So that's one option. But since we're in a theater, and since we're talking about active sensors, I wanted to show you a movie of kind of another little solution that I thought of that might even be a lot more fun had the designers and developers of CloudSat had the foresight to allow this capability. So the way CloudSat actually operates is it sends a pulse. Did I do that? It sends a pulse of radiation down, it bounces off the cloud, and we measure what comes back, and that's how we figure out what the cloud properties are. Now I was thinking though, if the developers would have been a little bit more, like I said, had a little more vision and decided, you know, we're going to need to resolve this discrepancy between what the different sensors think a cloud is. What if they would have given us the ability to point the satellite in different directions? And for example, shoot some of our competitors out of the sky. And so we could eliminate the competition using just electromagnetic pulses. And then next time Steve comes into my office or asks anybody what is a cloud, we can just all answer the same thing. This is obviously what a cloud is. Story over. So, that's all I